Hello, welcome to the CFD heat transfer class project for 3D axisymmetric flow. So we're going to first select 3D axisymmetric flow, and we're going to change it to the symmetry about the x-axis. So now we're going to have we're just going to do half of a pipe here. So we're going to do this in sections for reasons that hopefully will become obvious. Let's see. So we want the pipe to be about 10 meters in length. So probably just want to make this just a little bit smaller here, so I can fit in the 10 meters. Okay, that should be good enough. And now we're going to make we want it to be about 0.3 meters in height. So I'm going to make the inlet here. And up here we can get the x and the z values of wherever the mouse is. So here we go from here, and then going to go up about 2.3 meters. Okay, close enough. That's one. And then we're going to go all the way down to the other end about, I forgot, let's see, we started at minus 0.45, so we'll go all the way to about positive 4.5. That'll be 9 meters, about right, approximately. Okay, and then we're going to stop there, and then we're going to continue for another meter or so. Doesn't have to be exact, about a meter. And then we come down here, and then we go all the way back along the center line here. Alright, so this is just half of the pipe, as I mentioned to you. In the axisymmetric case, the flow is symmetric about this x-axis here. So there's going to be the bottom of it is going to exist, but we're not going to show it now. But it's just going to be a mirror image of whatever is on the top. So we have our tunnel made, or pipe made. Now we're just going to mesh it. And I'm going to give it, let's see, a target node spacing here of, this looks very coarse, so let's cut it down to 0.05 for the target node spacing. And let's lock the nodes and apply. Oh, I gotta select everything first, right? Gotta select what you want to apply that to. So here we go, and then we applied it. So let me do it again. Okay, there we go, and compute. Well, that still looks rather coarse. 0.05, p.05, there we go, apply. And let's compute. And there we go. There's our mesh. For some reason, there's kind of a little strange thing happening there, but we won't worry about it. Okay, so now we go to physics. And since we're going to be having temperature changes here, make it non-isothermal, we're going to keep the flow. We won't include buoyancy effects because the 3D axisymmetric feature cannot handle it. So we keep non-buoyant, turbulent, steady state. And this is air that we're using now. So now for the boundary conditions, we go here. So we're going to make this the inlet, new region, and we're gonna, so that'll be an inlet. And we're going to impose a temperature coming in of 20 degrees C, okay, and we apply. Did I forget to go? I forgot to give it the velocity. Okay, here we go. Velocity of 3 meters per second. Apply. So there we go. So now this top boundary is, this entire thing is going to be a wall. Okay, so this will be a wall, new region. Just a wall, and we're going to impose a temperature here of also 20 degrees. Apply. So now we're going to do this wall here, and we're going to make that a new region also. This is also going to be a wall, but now we're going to make it's going to be the temperature 100 degrees C. And the reason we've done this is that we want the flow to develop over the first 9 meters or so, and then we're going to extract the heat transfer coefficient here. So there's going to be no heat transfer on this top wall because it's going to be at the same temperature as the air that's coming in. So 20 degrees C coming in, 20 degrees C here. This wall will now be 100 degrees C, and we'll measure the heat transfer along here once the flow is fully developed. Now this will be our outlet, new region. So this will be an outlet. And conservative is good, apply, and there it is. And this entire bottom wall is going to be new region. This will be an axis of symmetry, so we're going to call it symmetry. So now it knows that the flow is symmetric about that axis, and that below this red line is going to be a mirror image of the top. So we apply it, and then we are ready to go, and then we're just going to up the number of global iterations to 1,000 in case it takes longer than the normal 350. And I don't think we really need to do anything else. So now we go to solver, we hit solve, getting the camel humps, that's good. And then this went very, very quickly because the mesh was so coarse. So we hit OK there. Now we go to post-processing, and we want to see the, well, let's see the temperature. And shaded show the scale, apply. Okay, so there's the result, and just as you would expect, okay, here you've got the beginning of a thermal boundary layer, right? We've got hot temperatures near the wall, and then it's cooling off far away. But okay, so now we want to go to the analysis tab to measure the wall heat flux. So I'll go here, variable will be wall heat flux, and now we select the wall, which I believe was this one. Yep, that's the one. And now we just, it tells us that on that wall the average heat flux was, here we go, 386. So a minimum value of 378, maximum value of 394, 386. So you can also, if you move over, if you scroll over it, it'll give you right here, I think it'll give us the value. Yeah, there we go. Yeah, you can see it here where it says value at location. So it tells you the wall heat flux should be 0 there, right? 10 to the minus 14, well, pretty close. And there it is. By you got the value at any way that you wanted. So we're just going to use the average then. There you've got the heat flux, and that's it.